Before we get started too far, like I told you before, we're going to write all of the carboxylic acid derivatives on the top of our board, top of our paper when we get started. Hopefully you remembered an acid chloride came first, then anhydride, then ester / thioester, then amide, then nitrile. We're going to get started talking about acid chlorides first. And the first thing we'll do is naming acid chlorides. Blech. As I said previously, all acid derivatives are named by first naming the acid from which that thing came. So if we imagine this as a carboxylic acid, that's a 2-carbon carboxylic acid, and a 2-carbon carboxylic acid name is acetic acid, if you're talking about common, ethanoic acid, if you're talking about IUPAC. So according to my rules up there, this now becomes acetyl chloride and ethanoyl chloride. Yep, weird. If we name this guy as if this Cl weren't here, there were an OH instead, that's benzoic acid. Common IUPAC doesn't matter. So this becomes benzoyl chloride. Meh. So it's time to do a reaction with an acid chloride. We're going to do all 4 of these reactions with an acid chloride. So we're going to do those 4 reactions with this acid chloride. Before we get too far down the path of starting to react these things, well, let me talk to you about this list. The reason this list is this way is we said we wrote it from most reactive to least reactive derivative. A more reactive derivative can be turned into a less reactive derivative directly, meaning an acid chloride can be turned into an anhydride through a direct reaction. An acid chloride can be turned into an ester through a direct reaction. An acid chloride can be turned into an amide through a direct reaction. And a nitrile is just weird. It can't happen directly. We're going to talk about them, but we're going to kind of ignore them for a bit. However, a less reactive derivative cannot be turned into a more reactive derivative directly. What do I mean directly? Remember, carboxylic acids sat over here to the side. If you want to turn a less reactive derivative into a more reactive derivative, you have to detour by a carboxylic acid first. So you can turn an ester into a carboxylic acid and then carboxylic acid into acid chloride. You cannot turn an ester directly into an acid chloride, but you can turn an acid chloride directly into an ester. You can go down the chart. You cannot go up the chart without detouring through a carboxylic acid. So let's draw some mechanisms of these guys. There are 4 things here, and as I have drawn, you can turn an acid chloride into 1, 2, 3, 4 things. So that's where we're going. We're going to do mechanisms, so we're going to start over here on the right. This is an anionic nucleophile. We attack the carbonyl carbon like that. Whoops. We make our tetrahedral intermediate. And from this tetrahedral intermediate, we fold down and kick out our weakest base, our best leaving group. That's chloride in this case, because I'm reacting an acid chloride, which is the most reactive carboxylic acid derivative. So ta-da, I make an anhydride. Moving right along to this example down here. I have a nucleophile, so I attack the carbonyl carbon. Float electrons up onto that oxygen. What's different here and here, this is an anionic nucleophile. So I attacked, got to my tetrahedral intermediate, immediately ready to fold down and kick out my leaving group. This time I have a neutral nucleophile. So when I attack, I end up with a positive charge generated on what was my nucleophile. So that needs to be cleaned up before I have my tetrahedral intermediate that I'm aiming at. Some base in solution comes to clean up the mess. I got this guy. This is my tetrahedral intermediate I was aiming at. I fold down my electrons. I kick out my weakest base, my best leaving group. And ta-da! I make an ester. There's a carbon over here. One thing I could have done here to make life more complicated is this is an asymmetric carbon, so I could have added stereochemistry to my initial alcohol nucleophile. Did the reaction happen at that asymmetric carbon? Nope. Not a dang thing happened to that asymmetric carbon, so that alcohol stays exactly the same as it was before. And I was careful to draw it in the same orientation every time, so I can just keep my wedge. If you double check, this is R, so in the end it should still be R. Check, check. All right, next comes the amine. The amine is neutral just like the alcohol, so you attack the electrophilic carbonyl carbon. Fold electrons up to the oxygen. Make this guy. Just like our last example, we ended up with an extra positive charge after the nucleophile attacked. There too. Some base comes to clean up. There's more information about who that base is this time. Hold your horses. Some base comes clean up. This is my tetrahedral intermediate that I was looking for. That looks like this tetrahedral and that tetrahedral intermediate. I'm ready to fold down and kick out my weakest base, my best leaving group. Ta-da! It's an amide. All right, one more. Hopefully you know what we're going to make here. I've got neutral water that I'm reacting with. Attack the carbonyl carbon. Fold electrons up to the oxygen. Get this intermediate. This guy gets cleaned up by some base in solution. That's my tetrahedral intermediate that matches all my other tetrahedral intermediates. So I fold down and kick out my weakest base, my best leaving group. One thing to note in this unit, when you make a carboxylic acid as a product, you need to be aware of the pH of the solution. What? Yep. Unfortunately, you need to be aware of the pH of the solution. This just says water, so I'm assuming a neutral pH. So about 7-ish. And at a pH of 7, does a carboxylic acid keep its proton or does it lose it? It loses it because it has a pKa of about 5. So the proper product here is probably the carboxylate version because you're at a pH that's higher than the pKa of the thing you're making. Carboxylic acids throw a wrench in things because they have this acidic hydrogen. All right, moving on in our notes, let's make some polymers next. So students sometimes think polymers are difficult and they don't understand, how do I know that a reaction is going to make a polymer as a product? Well, I have a diacid, a diacyl chloride, and a diol. When both of your molecules that are reacting together are bifunctional, they have two reactive functional groups, and for our sake of polymer discussion, they're going to be the same type of functional group. When you have two bifunctional molecules reacting together, that's an indicator that you're going to make a polymer, because a reaction will happen on this end and this end and this end and this end, and so you end up making a long chain of molecules connected together. This pink guy is called a monomer. The blue guy is also called a monomer. And when you hook them together, you're going to end up making a polymer. So if you look back at our last example, when we had an alcohol reacting with an acid chloride, we lost an H from the alcohol and a Cl from the acid chloride. And we made a new bond between the carbonyl of the acid chloride and the O of the alcohol. So we make that new bond. We're going to make another new bond on this other side as well. I'm going to draw it in a weird orientation so that I can keep my counting easy. And it happens again on this side. And then I run out of space. Polymers are very large molecules. Polymer is many monomers hooked together. Monomer, monomer, many monomers hooked together. So I got pink, blue, pink, blue, pink, blue, pink, blue, pink, blue. Again and again and again, repeated. And it gets pretty big to draw that entire molecule. So instead, the polymer notation is to draw one unit of each monomer connected together. Put a long arm sticking out of both sides of brackets and tell me that unit inside the bracket is repeated again and again and again and again. That's a polymer. It's a polyester because it's many esters hooked together. If we take a look at the next example, it's a lot the same. I've got a diacid chloride, and this time a diamine. Diacid chloride, diamine, ding, 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 I'm going to make a polymer. I draw one unit of each of the monomers. If you look back at our last notes, you're going to lose one of the H's and the Cl. So we're still going to keep an H on both of those. We're going to draw that polymer connected to that orange diamine, connected to the purple part of our diacid polymer. Long arm in brackets, long arm in brackets. If this is a polyester, what do you suppose we might call this? A polyamide. So there are our polymers. Hopefully you kept up and followed along. Up next is naming anhydrides. Anhydrides are a little bit different from all the other derivatives in that there's always two sides to them. So an anhydride, you name each side separately, and then you combine it as an overall name. So this side is a 2-carbon would-be carboxylic acid, and this side is a 2-carbon would-be carboxylic acid. So it's a symmetric anhydride. So this 2-carbon carboxylic acid would be acetic acid, so it becomes acetic anhydride. That's the IUPAC name. A 2-carbon carboxylic acid IUPAC is ethanoic anhydride. This one over here is a little bit different because there's 2 carbons on this side and 4 on the other. So this side is acetic, common name. This side is butyric, common name. So put them together in alphabetical order. This is acetic butyric anhydride. If you did the IUPAC instead, over here is butanoic. Over there is ethanoic. So butanoic, ethanoic anhydride, because those first 2 words are alphabetical. Oddly enough, there are spaces between the butyric, acetic, butanoic, ethanoic, and anhydride. It's a very spacey name, these anhydrides. Ready to do some reactions with them? Hopefully from your list up top, you know that there are 3 reactions that anhydrides can undergo. Let's do them. The nice thing about this anhydride is it's a symmetric anhydride. There are 3 carbons on both sides of that anhydride. So what that means is it will not matter which carbonyl I attack. I will get the same products either way. If I have an unsymmetric anhydride, I will get multiple products from where each side gets attacked. So we'll start with the first example over to the right, and hopefully you can already predict what functional group we'll make. But let's go. Attack the carbonyl carbon. There's no acid catalyzed stuff here or anything, just attack the carbonyl carbon. No motivation, nothing. Attack the carbonyl carbon. Get this intermediate. The problem is this intermediate has a new positive charge after my nucleophile attacks. Some base, somewhere, comes to clean up the mess. To get me here. This tetrahedral intermediate is ready to be folded down and kicked out. I fold down my lone pair from oxygen and kick out my weakest base, therefore my best leaving group. And I get, ta-da, an ester. But in addition to my ester, I get a carboxylate. So if you look back at your acid chloride slides, we did not draw chloride as one of the side products. It was there, but we didn't care. The deal this time is we have a carbon-containing side product. And so we do try to keep up with all the carbons throughout the process. So that's why I draw this carboxylate. Should it stay as a carboxylate? Well, if there's no acid or base in my solution, I'm going to assume a neutral pH of about 7. So at 7, yep, this guy is negative. Carboxylic acids are going to throw a wrench into all of our plans this time as far as pKa acidity stuff is concerned. Up next is the amine. Attack the carbonyl carbon. Why did I attack that one? No reason, just because I had already attacked the other one. So I didn't want my arrows to all overlap. It's a symmetric anhydride. It don't matter. I make this intermediate just like before. I now have a positively charged intermediate where my nucleophile attacked. Some base attacks. Who's the base? Hopefully you know the answer to that. I'm not telling. This is my familiar tetrahedral intermediate. I'm ready to fold down and kick out the weakest base, the best leaving group. And I'm making amide in the process. Should this stay as an O- carboxylate? You betcha, because we actually say amines are bases. So yeah, it's going to deprotonate that. One more. Water. Attack the carbonyl carbon. Fold up electrons to the oxygen. It's symmetric. It doesn't matter which side you attack. Some base, somewhere, cleans up the mess. You're ready to fold down and kick out your weakest base, your best leaving group. Uh-oh, what's the deal here? I folded down and made a carboxylic acid, and I kicked out and made a carboxylate. Should there be a second reaction that happens? Yeah, because I'm in water, and only water, there's no acid or base present, I'm assuming a pH of about 7. So at a pH of about 7, that carboxylic acid H will go away. So really, I have 2 carboxylates in solution. If you're being asked to draw this kind of mechanism, I won't really force you to draw how that happens. More likely, you'll be asked to predict the products, and you need to predict the products in the proper protonation state. This reaction where water reacts with a carboxylic acid derivative is called hydrolysis. And hydrolysis of all of the carboxylic acid derivatives makes carboxylic acids. Hydrolysis of all of the carboxylic acid derivatives make carboxylic acids. So this is hydrolysis, ta-da, carboxylic acids. Well, carboxylates. Moving on to more examples of anhydrides, but this time it's a cyclic anhydride. Let's see what happens. I'm adding an alcohol to my anhydride. Alcohol and anhydride, you do need to know the mechanism, but if we just sort of reference back where we were, we will see that we get an ester and a carboxylate, where one side gets attacked, fold up electrons, some base cleans up, and then you fold down and kick out your weakest base, your best leaving group. This is a symmetric anhydride. So once again, it doesn't matter which side gets attacked, but just that one side gets attacked. This is a benzene, so it's a planar molecule. This molecule versus that molecule, it's the same. It doesn't matter. But I get this. Then what happens if I add some SOCl2 to this? Does SOCl2 react with an ester? Nope. Does SOCl2 react with a carboxylic acid / carboxylate? You betcha. So my carboxylate turns into an acid chloride from there. What's nice about an acid chloride? It's the most reactive carboxylic acid derivative. So I can go from here and turn it into something new if I wanted to. I could turn that acid chloride into an amide, for instance. All right. What's so different about just adding alcohol versus adding alcohol that has been pointed out to be in excess, as well as acid? There's some acid catalyst in this one. The first bit is going to be the same, that it's an anhydride. You're going to bust it open. You're going to make an ester on one side. The only difference here is when there's an acid catalyst, you're not going to make a carboxylate. You're going to make a carboxylic acid. Okay, so what? That's a big deal. That's not a big deal. It's just an H or no H. Well, the problem is now you have a carboxylic acid, alcohol, and extra acid. Carboxylic acid, alcohol, extra acid. You're going to do a Fischer esterification next. You could not do that up here because a Fischer esterification must be acid catalyzed. Must. Did you hear me? Must be acid catalyzed. It's almost like I was yelling at you in the classroom and everything. So with the acid catalyst, you're going to get this diester. Well, am I going to turn this into a polymer? No way. The alcohol that I'm adding is a monofunctional alcohol. The alcohol that I'm adding only has one functional group. In order to make a polymer, both molecules you're reacting with have to have two functional groups. So my anhydride busted open to give me two functional groups, but my alcohol only had one. So I make this diester, this big molecule, that's it, I'm done. All right, moving south. If I add this amine to the mixture, amines and anhydrides, they bust open that anhydride to make an amide. Like that. Should I make a carboxylic acid or a carboxylate here? Carboxylate, because amines are bases. So this is the product that I predict as the final product when I add that amine up there. But if I cook this, and I mean cook it a whole lot, cook it, and cook it some more. If I cook it, I can get another condensation reaction to happen. Condensation simply means losing a small molecule. I meant to say that earlier. All the reactions we have drawn a mechanism for today are condensation reactions. Loss of a small molecule. In all of those others, it was HCl that we lost in the acid chlorides. In the anhydrides from the previous slide, it was a condensation. We lost a carboxylate every time. This is a small condensation. You're going to lose H and O and maybe another H, maybe lose a water. You're going to get this guy. This is super weird. I know. Is this mechanism something that we know? No, it's not something that I will ask you to draw ever. This is not the best way to make a new amide bond. See this new amide bond? This is not the best way to make a new amide bond, but it's a way to make an amide bond. The better way to make an amide would be maybe something like this. Make it an acid chloride and then turn it into something like that. But it would have to be an amine here instead, or an amide, I guess. Hopefully that made it more clear and not more muddy. I'm not sure that it did. Anyway, that's all for the first and two most reactive carboxylic acid derivatives. We'll pick up next time with esters and amides and nitriles. See ya!